Hi everyone, thanks for coming. So today we're happy to have Yuqing visiting us from Peking University. She's currently an assistant professor in the Center on Frontiers of Computing Studies. She got her PhD from University of Michigan in 2018 and her bachelor's degree from the University of Science and Technology of China in 2013. She's interested in topics at the intersection of theoretical computer science and information elicitation, prediction markets, mechanism design, and the future applications of these areas to crowdsourcing and machine learning. So let's hear her talk today about dominantly truthful multitask pure prediction mechanism with a constant number of tasks.
Thanks. Okay, so thanks for the introduction. It is my great pleasure to give a talk here. So today I will talk about my recent work on information elicitation. Let's start. So let me first ask you 3 questions. Do you like McDonald's? Do you like Subway? And do you like KFC? And the problem is, I really want to incentivize you to provide honest reviews for these 3 questions. And one thing we can do is maybe we just design proper reward systems to incentivize you. Okay. And here are several ways we can try. First, maybe we just check each participant's answer with some probability and provide her $1 if she can pass the check. But we can see here it's impossible to do that because illicit information is actually subjective. There is no way for you to check the answer. And the second thing we can try is if there are 2 participants here, we can pay them according to the number of agreements they have. So basically the number of restaurants they both like. But here we can see it's going to discourage minority. And moreover, it's going to encourage them to always report the same rating for all the restaurants, which is uninformative, but gives them a highest amount of payment. So that is the best thing for these 2 traditional reward system. And that is this work's contribution. So this work actually provides a novel reward system. First, it is strategy proof. So even you're the minority, so regardless what other people are going to do, for you, the best strategy is tell the truth. And it's actually strict dominant strategy of truth telling and the strategy that has the same amount of information with truth telling. So this is good. And second is the implementation of this reward system doesn't need any prior knowledge. You do not need to do any study for the restaurant you're going to ask. So that is the second good thing. And third thing I highlight here, because there are several previous works they achieve the strategy proof and prior independence, but they all need to ask the participants to answer infinite number of questions. So that's the main drawback. And this is the first practical one, which only require each participant to answer 2 C tasks. So C here is the number of choices. If it's a binary choice question, we only need 4 questions. And if it's like A, B, C, D, we only need 8 questions. So that is a good thing for this work. Okay. And also, this work also proposes a scoring rule such that it can identify the high quality information without the full knowledge of ground truth. So if you have ground truth, definitely you can know who is good. You just compare the agreements between their feedback and the ground truth. But when you do not have access to ground truth, this work is going to show you a way to do it. So far, any questions for previous? Okay, so before we talk about the solution, so let's set up the model. Okay. So basically, there are several similar fast food restaurants here, and we have 2 participants, Alice and Bob, and then they rate these restaurants with like maybe some up and some down, and then this is our goal. So we are going to design a proper reward system to take their ratings as inputs and then output proper rewards for both of them. And that is all we need to do is try to design a way to reward them. Okay. And here are several notations. And there are T restaurants, we assume, and with the reviewer space C. So in the binary case, it's like good or not good. So it's like, And we assume that we denote Alice's honest reviews by this small xa1, xa2 until xat. And remember that their honest reviews are known to us. So what known to us is actually their reports, which I put a hat here because that may not equal to their honest reviews when they tell the line. And we have a similar notation for Bob. Okay. And now I tell you what does peer prediction mean in the title. So peer prediction just means that every participant's reward only depends on her report and her peer's report. So basically, that is what this is. Only depends on their reports and no other side information to consider. Okay, and then this is the strategy definition here. So for each restaurant, for Alice, we assume her strategy is a C times C transition matrix. So here is a binary case. So this is a 2 times 2 transition matrix. So basically, this example means that conditioning on Alice hates a restaurant, with 0.8 probability, she tells the truth. With 0.2 probability, she lies. And conditioning on she likes a restaurant, with 0.9 probability, she tells the truth. So like, we just represent her strategy as a transition matrix here. Okay. And here are several examples. So you can recall the previous example. When they tell the truth, this transition matrix is actually an identity matrix because they always tell the truth. And if they always permute the answer, they just do this permutation thing. And this random guessing means that she will ignore her own opinion, and she always says she hates the restaurant with 0.3 probability, and she likes the restaurant with 0.3 probability. And this means that regardless she likes the restaurant or hates the restaurant, she always says she likes the restaurant. And this is mixed strategy. Actually, everything is mixed strategy. The special thing of this rule here is just first, it's not pure strategy. Second, the first line is different from the second line. And the reason I list these three lines here is because the first strategy is actually a fully informative strategy. Although for here, she just always flip her answer, but that is still from information theory view, that is still fully informative. You can just find the right way to interpret her opinion. And this one is uninformative at all, because like she just ignore her own opinion and always do the same thing. And for this one, it is partially informative. So, with that. Okay, so after to talk about the definition of the strategy, the setup of the model, so let's see what are the three assumptions we will make. So the first assumption, it just means, I think you already noticed that the restaurant, the fast food restaurant, we ask them, they should be similar with each other. So in the sense that they should have the same prior, the same joint distribution over Alice and Bob's honest reviews. So in a learning language, it just means that their honest reviews are IED samples. So actually in the original version of my submission, I use the example like, do you like Panda Express? And the second example is, do you like Chick-fil-A? And then the reviewer strongly insists me to change the example because these things, they are not a priori similar. You get it? Okay. And the second assumption we're gonna make is not only we need their honest reviews are IED, we also need their reported reviews IED. So that is kind of, we need them to play the same strategy for all tasks. But this same strategy can be mixed. So they can say with 0.5 probability, I tell the truth. With 0.5 probability, I just random guessing. It doesn't matter. And that is to imply these are IED samples. And the third one is we need to assume that their honest reviews are strictly correlated. So it doesn't mean we need to assume they have similar tastes or they have some we don't need to assume the information structure. We just need to assume they're correlated, they're not independent, and they are strictly correlated in some way. Anyone has a question for this three? Okay.
So in 1.2, A and B can be different, or?
Yeah, they can be different, doesn't matter. They just for each of them they should. Yeah. So here is more formal definition for strictly correlated. So basically, we just represent their honest review, the joint distribution over their honest reviews as a matrix. So basically, this matrix means that for a random restaurant, with 0.3 probability, they both hit it. And with 0.2 probability, they both like it. And this matrix can be unknown, it doesn't matter. But we just need to assume that this matrix determinant should be non-zero. And in this case, this is not allowed because their honest reviews are actually not correlated at all. So that is not allowed. And this is our definition for strategy proof here. We need the truth telling and also the permutation you have already seen. We just need the fully informative strategy being their strictly best strategy. And that is our definition. And there is also an approximate version here. So basically, sometimes you may not achieve the fully strategy proof, and you may want to find approximate version. Basically, it's just like with high probability, truth telling is greater than other strategy minus epsilon. So the mechanism we're going to talk about today will not use this definition. We just need to use this definition to describe the previous work. Okay, so let's talk about the previous work. So the peer prediction literature starts from 2004. It's from Miller, Resnick, and Halder, and actually Paul is also in Michigan. And this starts the first definition of the peer prediction. So what they do is they try to find a mechanism that is better than majority vote. But their mechanism have the strong weakness is they are not prior independent. Their mechanism need to know the full knowledge of the prior. And then in 2013, Dasgupta and Ghosh, they start the first multitask peer prediction. So basically for this one, they only ask people the single question. And this one, they ask people several similar questions, like the restaurant review case. And their mechanism is truth telling in the straight equilibrium and also the best equilibrium. But it just means that given other people tell the truth, for you, even you are the minority, the best thing for you is tell the truth as well. But definitely it is not. They cannot achieve the strategy proof. And another thing is their mechanism only works for binary choice. And the mechanism we're going to present today is actually works for a non-binary case. And moreover, they need to assume that the participants, their opinion should be positively correlated to each other. Okay. And there are several works they actually they achieve the strategy proof. But you can see that to achieve strategy proof, they all need the participants to rate infinite number of restaurants. And if they want to get a finite version, they need this sample complexity here, and they can only achieve approximate strategy proof. And we may be curious why this mechanism they need infinite number tasks. So here are some explanation. So they kind of want to know how to pay Alice and Bob. If they have similar tastes for the restaurants, they should be rewarded for a number of agreements. If they have negatively correlated, they should be paid for a number of disagreements. And in the binary case, there is only this positively correlated, not negative correlated. But in the non-binary case, it can be complicated. So they kind of need to use this infinite number of tasks to learn this taste structure, this information structure between Alice and Bob. and then pay them according to their learned information structure. So the gap here is like no previous strategy proof mechanism can work for a finite number of questions. I mean, in a not approximate version. And this work actually fulfills this gap by you can do everything, it's only to see. And finally, let's see the solution. Any question for previous slide?
That's a question. Previous slide, yeah. So for the previous results, the dominant truthful theorem, is the big O hiding a C in there, or is there any dependence on C in that sample complexity?
Because they actually consider like, I mean, C is small, so they just like,
Okay.
Yeah. And I think the mechanism they propose in their paper is most focused on binary case. So, yeah. But I think they can work for non-binary case. Yeah. Okay. So this is the idea. So basically, we still want to pay Alice and Bob some clever notion of agreements, but definitely not the number of agreements. So we want the expected payments for them to be a kind of mutual information between Alice and Bob. So what kind of mutual information? So first, we want this. So this mutual information is a concept here. I'm not like just referring to the Shannon's original one. So we want this mutual information being information monotone. It just means that, so remember, SA here is Alice's strategy. So when Alice performs a strategy on her report, we want the mutual information between her report and Bob is less than. So this property is just to get a strategy proof. And if we can get that, we can easily get strategy proof. That's easy. But the problem is, how can we calculate the mutual information? That's the problem. And so the second property is we need to, so since we only assume the participants, they try to maximize their expected payments. So actually only an unbiased estimator is sufficient. So we just want an unbiased estimator with a small number of tasks. And let's see several candidates here. First, number of agreements. So this candidate definitely not satisfy the first one, because when you are the minority, you can definitely try to perform some strategy to make you get higher correlation with other people. And we can see that the Shannon's mutual information is satisfied data processing equality. Basically, it's just a different term for this information monotonicity. But the problem is, remember, there is a log there, and you cannot get an unbiased estimator of that. You need to steer a lot of tasks to try to estimate the mutual information. Yeah.
Did you already explain what Shannon's mutual information is?
Oh, I can explain now.
Oh, yeah.
So Shannon mutual information, sorry, I didn't put the formula here. So there are two random variables, x and y, and you know the joint distribution over x and y, right? And the problem is you want to know how correlated they are. So if they are independent with each other, and then they are the joint distribution is actually equals the product of their marginal distribution. Mm-hmm. So basically, Shannon mutual information is a way to measure the distance from their joint distribution and the product of their marginal distribution. And what they use is they use KR divergence. I don't know whether it can be seen as a distance. It can be seen as a metric to measure a distance between two distribution.
Got it.
Yeah.
Excellent.
So if you use the usual mutual information, what is the sample complexity you would get for unbiased estimator?
I don't remember, but I think it is very similar with this one.
Okay.
Yeah.
Can I ask a clarification about the model? What do the agents know about each other?
Oh, they need to believe that their honest review, the joint distribution of their honest reviews should be strictly correlated. That is, they do not need to know what is their, they just need to believe they should be strictly correlated.
Right, but do I know your strategy? Do they know?
No, they do not need to know that. They only need to believe that we all perform the same strategy for all questions. But I don't need to know your strategy. Yeah.
And one more question. So does the problem of selling become easier if the strategy, or no, actually the matrix that you're talking about, the noise matrix, is symmetric?
Say it again.
It's like symmetric. It's like a symmetric channel.
Oh, yeah. Symmetric is good.
It's easy. It makes it easier.
No.
Okay.
Yeah. But I mean, if it's asymmetric but still satisfies the information monotonicity, you can still get strategy proof. But symmetric can give you better property. Yeah. And so forget. So now the problem is actually we just need a new definition of mutual information to satisfy. First, it should be information monotone. Second, it should be easy to construct unbiased meter for it. And how? So let's just observe this strategy actually. So one observation we can get.
I'm sorry, more questions, sorry.
Yeah.
Can you go back to the mutual information?
Yeah, sure.
That's not what you want, right? So one, it should be for all S Bob, this equality holds, not for all Bob.
Yeah. Not for honest Bob actually. You can replace this honest Bob by dishonest Bob. It doesn't matter.
If you want dominant strategy, it does.
Yeah.
Dominant strategy says no matter what you do, I want to say the truth.
So actually, I
If you say the truth, I want to say the truth.
Yeah, you're right. Actually, I should replace this Bob here with Bob hat.
Right.
Yeah.
Okay.
Yeah.
Thanks.
So one observation we can have is like more informative strategies has a higher determinant, right? I mean, in an absolute way. So they have one, this is 0, and this is between 0 to 1. And that is basically the whole intuition of this. So why we cannot measure our mutual information using determinant? So basically, we have two random variable x and y. It's not like the traditional Shannon mutual information. We try to measure the distance between the joint distribution and the product of the marginal distribution. Here, we just write down this joint distribution as a matrix, as a square matrix, and we calculate the determinant. That's all we need. And what's good thing for this? First, it is information monotone. You're gonna see the proof in a later slide. And second, remember the determinant is just a polynomial of the the entry of the joint distribution. If it's a polynomial, you can easily get an unbiased estimator of this. But you're gonna see we have an absolute value here. How can we deal with it? Then you just square it. Then everything is fine. So that is like once you get this, it is nature to get this mechanism. So the mechanism is, remember, we want to pay them the unbiased estimator of the square of the determinant. So we first ask them to answer, like for example, 11 restaurants here, and then we divide these restaurants arbitrarily into 2 sets. And for each set, we count how many restaurants they both hit, how many restaurants they both like, and how many restaurants Alice likes when Bob hits. So this is just kind of frequency here. I call it answer matrix. And then you just calculate the determinant and multiply together. So we can see another intuitive reason we need two sets here is we want their payment being positive, right? In expectation. And if these have similar tastes, then definitely these matrices are kind of like diagonal dominant. So they have like positive determinant. When they multiply together, still positive. But here they actually have different, actually negatively correlated. And the determinant should be negative, but when they multiply together, it's still positive. So that's the trick. And it's not only for the binary thing. It's like for the non-binary thing, you just like do the same thing and calculate the determinant. So that is the basic trick of this mechanism. And in the 2 participants case, we reward them the same amount of payment, being the product of the 2 determinants. And if there are multiple participants, you can do something like you just pairwise them and average the pair. And we can show that when each set of the the problem's the size greater than C, this is a strategy proof. And the reason we need this lower bound here, because if it's less than C, and then the determinant will always be 0. So that's just why we have this 2C bound here, right? So for example, C equals 2 here, if we only have one question and we count the answer frequency for this matrix, then we can only put it in 1, and this determinant always being 0. So that is why we have this sample complexity. Okay. And now the proof is divided into 2 steps. First, we need to show the determinant is information monotone. And second, we need to show that we actually paying them the unbiased estimator of the determinant square. Anyone has a question about? How many minutes do I have?
Maybe
I see.
45-ish minutes.
Great. So let's first prove the first one. So this equation is actually important because I'm going to use it to prove some property of the scoring rule later. So basically, I want to show that the determinant mutual information between Alice perform a strategy SA and Bob equals to the determinant mutual information between Alice and Bob times we kind of find a way to measure the amount of information, the amount of information contained in the strategy. And then this is, we're going to show this is a real number between 0 to 1, and we can get this monotonicity. And let's see how. So the DMI between SA, Alice, and Bob equals the absolute value of the determinant of this joint distribution matrix over XA, Alice, and Bob. And with some calculation, you can show that this joint distribution matrix can be written as a strategy times the original joint distribution matrix. And then the good thing about the determinant is determinant A, B is equals to determinant A times determinant B. And this is a transition matrix. So we know that the transition matrix, their eigenvalues are bounded by 1. So their determinant is also bounded by 1. So we use this, we can think this determinant of this strategy being as the amount of information contained in the strategy. So remember the previous slides for that 3 line there. This kind of the determinant of the strategy represents the amount of information contained in it. And that's how we get. So it's actually, we just follow from linear algebra. Okay. And now this thing is a little bit subtle, but still you can do it. The second thing is you want to show that the payment we pay is the unbiased estimator for the determinant square. And basically, we just need to show that for each answer matrix, its determinant is proportional to the determinant of the joint distribution in expectation. And then when you multiply them together, it's proportional to the square, right? Because that is why we need 2 sets, because we want them to be independent. And then we can do the thing like EXY equals EX times EY. So, but for each answer matrix, we need to show that. So see here is a joint distribution matrix. We know that for random restaurant with 0.2 probability, they will report they both hit it. With 0.1 probability, they will report they both like it. And this is actually kind of sample from this matrix, but you need to times the number of total questions. The problem here, why I say there is a subtleness, it's not that direct, is because although in expectation, this thing divided by the number of questions is proportional by this thing, and this thing divided by the number of questions is proportional to this thing. They are true, but you cannot say that this times this minus this times this proportional to that, because they are not independent with each other. But the lucky thing is if you write down the formula similar very carefully, you can still get this property. And just omit the proof here. You can refer to the paper. But in fact, one thing I want to make the point is like once you already get a polynomial, format of removing information, you already know that you can get the mechanism. The only thing is just how you can make this mechanism be more pretty or something. Okay, so now let's go to the second result of this paper. Is what I said before, is I'm going to provide you a new scoring rule to identify high quality information without verification. So what I did is like very natural. We just like score Alice using this like the DMI thing between Alice and Bob and the DMI thing between Alice and Charlie if we have 3 participants here. And you can see why we need at least 3, because if there are 2, they always have the same score. You need 3. And what is the theorem we want to show here? So we want to show like why this scoring rule makes sense in some sense. It's like, for example, when there exists a ground truth G such that Alice, Bob, Charlie, they all are independent conditioning on this G. And then the problem is we still want to know Alice, Bob, Charlie, who is good, but we do not have G. All we can do is calculate this like DMI score, and we need to show that their DMI score actually reflects how close to G, but without knowing G. And let's see why this is true. So the whole trick here is like we can think. Like, for example, if we want to compare Alice and Bob, we can think Charlie as a noisy version of the ground truth. So basically, Charlie's report can be seen like you add some noise on the ground truth. And then when you like try to get the difference between Alice's score and Bob's score, so remember that the Alice score is the correlation between her report and Bob's report and her report and Charlie's report. And you can see that this determinant is metric. So you just like, so when you calculate the difference or you compare, basically it's the correlation between Alice and Charlie and Bob and Charlie. And that is one thing I say you should, we should pay attention is that the DMI score just because the determinant has a property DET-AB equals DET-A times DET-B. So we can like get this in like this informativeness of Charlie. And once you get this, you can see that they have some like one-to-one. Yeah, that's basically the trick of this. So although that the DMI between Alice and Charlie is smaller than the DMI between Alice and ground truth because Charlie is a noisy version. But it is only smaller in a relative way. So they are still can be relatively compared to each other. Okay. So let's see, like people can ask why this is useful. So one example could be in the learning. So let's see, Alice is classifier A, Bob is classifier B, and we want to know which classifier is better to predict, to classify to the clean label. But the problem is we do not have the ground truth, the clean label. All we have is Charlie, another version of the label. And in this case, we still want to know who is close to the clean label. So if we use already like the traditional cross entropy measurement, and then it's kind of like unfair for you to use this Charlie to, and if we use this, what I said before, the determinant trick, and then you can show that you can like evaluate the classifiers with only the access to the noise label. And this paper has been published in this year's New Rips. Okay, so it is a short talk. So let's see the conclusion here. So this book proposes a novel reward system that is strategy-proof, prior-independent. Most important thing, it is practical. And here are several future works. For the definitely we want to run real-world experiments to show that this thing, not only can maybe not incentivize people because people may not be that rational, but at least it can help us to know who gives you like higher quality feedback. So that is, and the second is I only interested in this from a theoretical view is can I fully characterize all strategy proof mechanisms in this setting? And maybe I can do some optimization there to see like which one, if I want some property, I can just optimize over this family. And second and third thing is that actually many people ask me, so they think the ID assumption is strong. So one way is like, can we relax the ID assumption in some sense, or maybe in a different setting? And the last thing I'm interested in is like, is 2C the best? Like, can we do better than 2C? Okay. And thanks for listening.
All right, we have plenty of time for questions.
Can you go to the slide where you define DMI for the first time?
You want DMI? Oh,
Yeah.
sure.
Yeah, that slide.
You mean the DMI mechanism
Yeah,
or
the mechanism.
Mechanism.
My question was,
Uh-huh.
do you have to pick T1 and T2, or what exactly are T1 and T2 again?
Oh, the T1 and T2 are just two sets of questions. So, for example, there are 11 restaurants here, and T1 is like this first 6 restaurants, and T2 is this last 5 restaurants. And you do not need to pick them. You can pick arbitrarily as long as their size, each of their size is greater, is at least C.
C being the number of
Choices. Here, C equals 2.
C is equal to I see.
Yeah.
And why do we need them to be at least C?
Or it's just because like if it's less than C, the determinant of this matrix must be 0.
C must be 0. Oh,
Like
yes.
let's say like if C equals 2, if there's only one thing you need to put it like
Yeah, you're right.
Yeah, yeah.
It's guaranteed to be 0.
yeah.
Cool.
So I had a question regarding this. So if C is large, then with really high probability, it's going to be 0 determined anyway, right?
Yeah, I actually have a concentration bound analysis in the paper.
Okay.
Seeing like you need to if C is large, it's kind of if you want to get more concentrated, you just need more. Like,
So like roughly how many tasks as a function of C? Like how fast?
I don't remember. It's
Okay.
like I just use simple second moment analysis. Maybe I can do better.
But do you think it'll be better than 1 over epsilon squared, the other bound?
It's a good question actually. I didn't compare. I should. It's kind of like a little bit cheating here. It's like if we care about mechanism, we only care about the expectation. Yeah.
So
Yeah.
beyond the math, like how is it not an equilibrium for both of us to say, to pretend that the truth is, whatever maximizes our payment? Like something about this is
I know what
bothering
you
me.
mean. It's like
The outcome, like whatever you think is the truth at the end or whatever, is like my utility when you believe that my belief is something is not affected at all by what my belief is. So why wouldn't I pick the strategy such that after I apply the strategy on my truth, I get the thing that maximizes my payment? Does that make
yeah,
sense?
so
It's
I know what you mean. So the thing is like remember the definition of this strategy. So all I do is I just like apply this strategy on my truth. So it's kind of like you cannot do whatever you want. You cannot know like so.
But okay, I'm not allowed like things. Remember with the determinant 0 in my strategies, but I can be almost there. Like that's
Yeah, that's not the
close as
problem. That's
possible.
not the problem with determinant 0. It's just like I can do whatever I want to do, but the thing is, all I do is based on my private information, my private signal for this restaurant. So, for example, if like I rate these 3 like restaurants, like the McDonald's, like this, and for Bob's information, all I know is that for each of the restaurants with like maybe 0.3 probability, he say yes. With 0.7 probability, he say no. But I don't know which restaurant he gonna say yes, which restaurant he gonna say no.
Right, but I'm saying it's an equilibrium. I'm not saying it's not like I'm saying like if we both say we hate everything, so
Yeah,
that
that's
we
narrow.
get something,
Nothing.
right?
No.
Sure, we get no payment. Okay, so now we're the opposite. I always say I hate. You always say you love everything. Then we get some payment.
Oh, that's
No,
zero.
that's also
Again,
nothing.
Again, zero.
Because you just fill one corner of that matrix and the determinant is zero.
Zero.
Again, zero.
Again, I'm not allowed to sample at random because that's not informative. I'm just saying, like, there's some things I can say that maximize my payment,
No, wait,
like the
you-
combo of what we can say maximize our payment. So how is that not an equilibrium? Like precisely the reports that maximize
No, I think
our payment.
only equilibrium
How is that not an
tell
equilibrium?
the truth, right? Because truth is
Dominant.
dominant, yeah.
It's not only like if you
Oh,
first
the-
permute the answer, it's also a
Yeah, under permutation. Under
Yeah.
But I think
the
under this,
permutation.
permuting is telling the truth.
Yeah,
right?
yeah, permutation.
What if the truth is that I hate everything?
What is it? What?
What if the truth is that I hate everything?
Oh, that can't be. So there was an assumption that prevented that we both always
Almost
Always-
everything.
yeah, yeah.
because that has the zero.
almost
Prior
everything.
assumption.
Yeah,
Yeah. So you assumed we didn't start with determinant zero.
Right, but it could be I hate almost everything and you love almost everything.
That's fine.
Yeah, that's fine.
So in the samples, like you see that I hate everything.
Yeah, so you're gonna get like really low expected
Yeah.
payoff, I think, but you're still
It's been on zero.
incentivized to do the right thing, but like really small in proportion to the information.
Yeah.
But I can see here. I guess it's just bizarre. Like it's bizarre that if in reality my probability that I don't hate something is like epsilon, and it's the same exact thing for you, which is a valid input. I know with tremendous probability the honest samples will show you is like all zeros, and that will pay us nothing. So like before I say the last zero, I'm just gonna say 1. How come I don't want to do
I feel
that?
like that's a critique of the assumption where like you should just change your strategy for different tasks.
IID. So
Yeah.
So I think your complaint is
So that where does that come from? Like I'm just saying from the IID,
The
or
IID
that's from
thing.
the expectation works out perfectly.
The
Or the
assumption
IID.
two, I think, the assumption two.
assumption two.
That is the
Yeah,
strategy for
everything.
timestamp.
Yeah, the second assumption too.
I see.
Yeah,
Assumption 2. Okay, assumption 2 is what I did.
Exactly.
Okay, good. Sorry. That okay. I'm okay now.
Interesting.
I have a question. So, under some additional assumptions, can you show, is it possible to show that the DMI mechanism is unique?
I think that multiple property is like multiplicative property that times the informativeness thing. I feel like I can show
Should be,
that.
I see, okay.
Yeah, but for this, I think I've already construct other mechanisms have the same property. But the thing is, they all have the higher degree than DMI. So I feel like maybe DMI is the lowest
degree.
Yeah.
Sorry, what do you mean by degree?
I don't know.
Oh, it's just like it's a
How complex to
phenomenon.
estimate?
It's a
that,
phenomenon. Yeah, sample complexity.
Okay.
But maybe I'm wrong.
All right, great. Let's thank the speaker once again.